Good morning. Bright and early Saturday morning. We'll get through this and then you can start your day. So last week I I asked you to review the notes up until here. And I guess I need to know how many of you did that. Good morning. So we have 2 classes before the test. So we have lots of time. We have today and next class, and one more even before the final. And what I'm thinking to do is today we're going to look at this unit, in Unit 5, this section, SDS, and then start inference. And then I have these 3 weeks for Unit 6. But there's a test on May 1st after class, right? And I want to be sure we'll do the test from noon till, I can give you more time. If anyone objects, they can let me know. I just don't want to give you too much time that you waste your day. You should be able to do the test. If I said 4 p.m., or do you guys prefer 6 p.m.? Let me know. Okay, Nicole would like more time, or she said she'll take as much time. I don't I don't mind giving more time. I just wonder if people feel disadvantaged because they have other commitments. That's what I'm worried about. I can leave the exam 12 till 6, but if you started at 5, then then you're in trouble again. But I can do that. And the solutions will not show for students until the next day. I'll show you the answers, the actual answers. You'll get your grade, but you won't know which ones you got wrong or right. So if anyone objects, let me know. So let's see, we'll confirm next week, but just let me know if anyone objects. Write me. Any other questions before I start? I'm going to wait for a few more people. Oh, you can't see what I wrote. I said, oh dear. And this is for test 3. And then there's a final exam that we're going to have, which will cover everything, and it will be Yeah, it'll be a little bit of everything. The final test, you can practice for this final test using the final review documents that I have in the section on the final exam. This is going to be on May 1st, right? May 1st. And then the final test, I would like to have it on, I think we're supposed to have it May 15th, because that will be the last Saturday before grades are due. So it will have the same format, sorry, not same format, but I guess distribution. Okay, I'm going to write down to see what it's called. The document on Moodle is called approximate. I'll write it in red. Approximate distribution. Actually, let me pull it up. Let's see if I can pull it up. Still waiting for people. It's only 9. Okay, I'm going to start in a few minutes. Let me just do some housekeeping. Answer some questions about the tests. So here's the course, and down here, go to final exam review, and in final exam review, you see you have this document called approximate final exam distribution. In addition to having these review exercises, so you have the review questions for the final, and then you have practice assignments for the final, and then you have this document called final exam approximate distribution, and it tells you how much of the test comes from each unit, okay, or each section. So you can see I only include about 10% in the first 3 units. And then remember, this is for the final. And then 20% for probability, 10% for bin, but I say omit continuity correction factor, although I'm going to teach that right now. You don't have to worry about it for the final, but you should understand the concept. What we're going to do today is 20%. And then what we're going to spend the rest of the time doing, the next 3 classes, is on the last unit, inference. And I tell you, you can omit some pages that are just there for completeness. They're going to be, oh, I don't know if that's going to be true. I actually should fix that. Well, maybe I can stick to it. 16 multiple choice question. Okay, it's all going to be multiple choice, so I'm going to change that. I have to fix this because I'm going to make it all multiple choice, or maybe I can stick with, anyway, I don't know, maybe I can stick with this. The thing is I have to grade it. That's the problem. I have to find time to grade it. Maybe I can. Maybe we'll stick with this. So this will be 16 multiple choice questions, and then you get to choose 5 out of 7 problems, and you have to solve them and send them to me, and then you have to send me the last point is a short answer question that comes from Unit 4, pages 42 to 48. So it's one of those long problems where you have to apply the rules of means and variances. Okay, so you have to pick, I'm going to pick one question from those and adapt it a little bit, and that'll be on the test. So let's stick with this format. It's worked in the past. So I will grade your final exam, 60 multiple choice questions online, and then these others will be for hand-in. And that will be similarly I will do that from you can have from 9 a.m. I mean, I can say till 6 p.m. I don't mind. So that's your day on May 15th, 9 a.m. to 6 p.m. to solve that test. Multiple choice questions and hand-in problems. I still have to mark it, Gerardo. If I make it all multiple choice, I still have to mark it all. So what else you have on the, so yeah, it's just that the structure of some of the final tests, you know, the format that I give you is reinforced with what I call the mock exam. So you can practice on the mock exam for the format. So this is the mock final, and this shows you how it will be in questions similar to what I'll ask. So you should practice this on your own, and so sit with this exam for at least, you know, give yourself about 3 hours and see how you perform. You see, so there's the, you get to choose. Let me show you, let me pull back. So those are the multiple choice, and then I say choose, answer only 5 of the 7. So you get to pick which one you want to answer, but you should practice using all, answering all of them. And then this is the third part, is where you have to answer this question that is one of the questions from the notes. I'm going to vary it a little bit, but you need to know how to answer that type of a question with means and variance rules. I will give you the formula sheet, which you have in your notes anyways. Okay, so you can work with that. Okay, so that's what we're going to do. So May 1st will be the third test. May 8th will be a class. And then May 15 will be the final exam. And the mock exam will be available what's going on? the mock exam is available already in Moodle, and I just have not shown you the solutions. The solutions are hidden. So I'll open those up closer towards the exam so you can see if you've got things right. I prefer you try the exercises before you have the solutions. It's really meant to be a mock final, so you get to practice, identifying where you have difficulties and struggle a bit to learn that about yourself. And then I'll give you the solutions. Any questions? Okay. How's the sound? Okay, so you can take a screenshot of that because I have to move on. Start class. So how many of you were successful in reviewing the notes up to here? Anyone want to let me know? Yes. Oh, good, Gerardo, I'm glad. So I gave you an instruction to look at these without me, but I feel I need to backtrack a bit, but you would be better off if you actually looked at it. This is where we left off last class, and I explained to you that binomial distributions are not necessarily symmetric. They will be symmetric if your P is 0.5 or 50%, or if this property is true, if n times P is greater than 10 and n times 1 minus P is greater than or equal to 10. So if these properties hold, then what happens is your binomial distribution appears symmetric, but more than that, it is approximately normally distributed. And the mean is computed as NP, and we discussed why, and you can look that up again if you don't remember. And then I proved as well, actually I proved, but I didn't talk about it last class. There's a proof in the notes about where this comes from. This is the standard deviation. The proof is right here. And I'm not going to go through it, but you should be able to read this. You should be able to go step by step. This is an application of rules of means and variances. You should be able to follow this. Okay, so read through that and see why the mean is n times P, and the standard deviation is that. The square root of the variance. The variance is computed as the sum of trials, right? The sum of the results of these Bernoulli trials. Each time you repeat the same thing and check, is it a failure or is it a success? And so when you calculate the variance of a sum of variables, you just get the sum of the variances as long as they are independent. Right? So that's the rule. They are independent because they're independent trials. That's the key word. So independent trials. The variance of each of these trials is the variance, but the variances are all the same. For each trial, the variance is derived above. Do I have it above? Yeah, it's up here. So step through this and figure, it's not hard. This is just some math, really. The statistics is here, but the math is here. And then you can see that you're just summing these variances, and there's n of them. So that's the variance of the variable x, the number of successes in n independent trials. So x is just counting the sum of those independent trials. So that's the variance. So you have to take the square root to get the standard deviation. So read through that. If you have any questions, let me know. And you should feel comfortable that for a binomially distributed variable, its mean is NP from the argument about that we made last class about using the example of a basketball player. If he throws the basketball 10 times and the chance of getting it in the basket is 80%, then you would just multiply them to know, how to predict how many he actually gets in. So that's why we multiply logically, and then I actually prove it in the notes. And this is proven as the variance, square root of the variance. So that's the mean and standard deviation. I put them here, and I use this symbol to say approximately. So we can convert the binomial distribution, which is a discrete distribution with a spike graph, we can convert it into a continuous distribution with a smooth curve in approximation. So this is what we're looking at. As explained above, provided n and p are such that both n times p is greater than or equal to 10 and n times 1 minus p is greater than or equal to 10, then the normal density curve can be fit to the binomial probability distribution. So this would be the binomial, and what we're doing is we're forcing, okay, it's not going to look so good when I do it. Let's do a thicker marker. Okay. You get it. So I'm fitting that normal distribution, and you notice there's some gaps here and things, but it's approximate. Okay, it's approximate distribution. And so what we do next, we no longer have to use the binomial formula. We can count on, hold on a moment. I had to cough. We can count on the normal distribution. So for instance, let's take this example of a variable hex being binomially distributed with 100 trials with probability 1/3 of seeing a success we're interested in, and we want to find the probability that there are more than 23 successes out of 100. Well, this would mean we would have had to add all of the probabilities, x equals 24, x equals 25, all the way to x equals 100, which is tedious. And if we're doing this manually, we can make a mistake, right? We can make an error. It's using something like this can get us just pretty close, and let's try it. So let's see. What it means then is first we have to check if we can use the property of the binomial distribution. Oh, let me say here, in fact, what I did here was show like the threshold, like this distribution here where n is 20 and p is 0.5. It's going to be symmetric, but with n equals 20, it just satisfies this rule, right? Because 20 times 0.5 is 10. And then again, this would be 20 times 0.5, which is 10. So it would this just satisfies the rule. So starting here with p equals 50%, as long as there's 20 trials, you'll get a bell-shaped, approximately normal distribution. But if p is not equal to 50%, it could still be true. So this was an example. Here, p is not equal to 50%. It's 1/3. And we're going to check if, in fact, it satisfies that rule. So when we check, 100 is high enough to make this 33.33, which is greater than 10. So that's true. And then we have to multiply n times 1 minus p, which is even greater. So that's greater than 10. So that means that we can use the normal approximation. All we have to do next is find these values, these parameters. So so let's find the mean. That's just going to be n times p. So I multiply those together. I already had that actually from above. And then for sigma, for the standard deviation, remember I use the subscript x just to remind myself that this is coming from a binomial distribution. And we multiply n times p, 1 minus p, and take the square root. So there it is, 4.71. So what we found are the mean and the standard deviation. So we put them in here, and we use the symbol for approximation. And then we can answer the question. So now our question, rather than adding the results of using the binomial formula for each possible outcome, we go back to the normal distribution and instead standardize our variable x. We standardize x and convert it into a z. So we standardize 23 as well, minus the mean divided by the standard deviation, and here we get an answer. So this is a faster way to get the result in approximation. So if the probability of a success is 1/3, and you try 100 times to look for that success, the chance that you get more than 23 successes is very high. It's almost 100%, right? It's 98.57. So this is important for making predictions. This is important for, and you can feel it, like this is like in selecting, okay, let me say this. In these problems, I'm giving you the mean and standard deviation. We're building this theory where I give you the mean and standard deviation so that we can use this. So sorry, let me step back. I give you the parameters for the binomial, and then you calculate the mean and standard deviation, and you can use them. We build this, we have built this theory, and I'm just showing you how to apply it, but it depends on actually knowing the parameters. Okay, I actually have to know these. Well, in reality, I don't know those, right? So everything that we've done in this course so far is leading us, we've built this theory so that we can deal with situations where we don't know the parameters, and we can estimate them through inference. So everything that we do builds a toolkit for us to do inference when in reality we don't have these available to us. Okay, so we're just practicing, we're practicing with the tool, right? That's what we're doing right now. When we do have them, this is how we could solve it. All right, so this this technique ultimately helps us answer the initial problem. What is the probability that someone who is simply guessing will be found to have ESP? Well, remember the parameters, right? P is 1/4. We did this already, and we know n is 100 attempts. So x is binomial with 100 1/4 is the probability. The ultimate question here is, what's the chance that you'll be found to have ESP? And we would have to add together all the probabilities from our table to find that. And that's tedious, and we can make, if we do it manually, we can make an error. So let's look for a different approach, and here it is. We're going to check whether we can use the normal approximation. So let's see, is the rule satisfied? N times P is 25. Yes, that's greater than 10. So that's true. And then n times 1 minus p is equal to 75, which is greater than 10, which is true. Makes that true. So then we know that we can use an approximation with the mean of 25, which I calculate here, and a standard deviation of 4.33, which I calculate here. So practice making those calculations. That's what I wanted you to do over the weekend or over the week, because it doesn't help you for me to make the calculations. So if you haven't done it, go back and do it, but just follow with me for now. What we do next is standardize, right? We have the mean and standard deviation. We can standardize this problem and find that, well, this is way off the table of standard normal. So this is going to be 0. So the chance that someone just guessing will be found to have ESP is so small, it's 0. Okay? Any questions before I continue? So should I let you have a minute to punch that in, make sure you can get those calculations? You can infer it because of the question, for sure. You can say, what is the probability that someone, remember in the problem it did say that if a person guessed 50 or more, it was part of the problem. If a person guesses 50 or more correct, they'll be found to have ESP. So that was defined. But thank you for asking to clarify. Go look back at that. So you would have to be given that for sure. Okay. So I'm just seeing if you can punch those in. Make sure that there's a catch here. When you punch this in your calculator, just remember to say 100 times 0.25 times 0.75 equals, and then the square root, or you will not get the right answer. Depending on your calculator, that will be safe doing what I just said. But make sure you can punch that in. Or use Excel. All right, let's see. So, hopefully you follow that discussion, and I'm going to build on top of it. Let me show you the formula sheet that we're working with. So we've done, last week, we already discussed this, right? We discussed the binomial with parameters n and p. Then x has mean. This is like almost the last page of the notes. The mean is np and the standard deviation is np, 1 minus p with a square root. And this is the binomial formula. And I mentioned here, x is also approximately normally distributed provided n times p is greater than or equal to 10 and n times 1 minus p is greater than or equal to 10 and the population size is large. So those are the criteria to be able to do this, which I've put onto the formula sheet. So large means it's large enough, and we'll just stick with problems expressing that it's large. This is not really a good approximation when the population size is small, turns out. So you'll be told it's large, or you will assume it's large, unless told otherwise. Okay, so we're getting now then, we finished the first formula. We're into the next one. Now what's all this about? Given x is binomially distributed with parameters n and p, the sampling distribution of p hat equals x over n has a mean of p and a standard deviation of p, 1 minus p over n square root. So I need to discuss this. And notice I've repeated what I have here in terms of assumptions or properties. So where does this come from? 2 comes directly from 1. I introduced the idea, let me say here, we're going to call this, I will refer to x as a count variable. I often say that. X is a count variable. And what we're using for number 1 are the properties in the bin nodes. But also, it's not, I don't spend too much time on it, but it also overlaps with SDS. What is SDS? SDS stands for sampling distribution of a statistic. Sampling distribution of a statistic, and that's what we're going to talk about now. So given that x is binomially distributed with parameters n and p, say we were given information on a simple random sample of size n, which we can count the number of successes. So that's pretty much what we're doing right above. So if we have that, then we could also compute the proportion p hat. P hat is just the number of successes divided by how many trials were attempted. P hat is a statistic because it takes the results from a sample. It takes the findings, the data of a sample to be computed, okay? So you need the data from the sample to compute it. So that satisfies the term statistic. So the sample proportion, like the other statistics we learned, mean mu is estimated by x bar, and the standard deviation sigma is estimated by s. Those are the population parameters. P is the proportion of the population and it's estimated by p hat. So don't let that confuse you. P hat is a statistic like S, and X bar are statistics. Whenever you have a hat on it, it's an estimate. It's a statistic, usually. So the point I'm making here is, what does it estimate? As a statistic, it estimates P, the true proportion or the population proportion. So, for instance, let me go back. Actually, let's see. So, if I take that problem that we just did together, and I'll talk about the above in a moment. If you take the exercise that we just did, where we were given 100 trials and the chance of a success is 1/3, find x greater than 23. And we already solved it. We already did this. We already have an answer. But I want to show you I can recast x rather than as the count or the number of successes in n independent trials, where this is also like a sample, right? It's like a sample. It's like n trials. I see how many I got, you know, what I'm looking for, and I can talk about the count, or I can recast that as the proportion of successes. So all I'm doing, this is the number of successes, and this is the proportion of successes, or let's write percentage. So you've seen me do this before. It's making it a relative measure, right? It's a percentage. So I'm putting the total on the bottom and I get a value. Not such a big deal. What does that do to the results? What does that do to the mean and standard deviation? If I divide x by n, do I just divide the mean and standard deviation by n? That's what's at issue. Well, because of the rules of mean and variances that we discussed, the fact that we have n independent trials makes it true. So we just get these results where we have x, right, approximately normally distributed with mean of NP and standard deviation of NP 1 minus bx, what we found here is x's sampling distribution. We found out the pattern of the possible outcomes for x. This is a sampling distribution. So without even realizing it, that's what we found. So this is the sampling distribution. That's what it represents for x. Now let's get the sampling distribution for p. If we divide x by n, because of the rules of means and variances, we can divide the mean by n. We we can divide the standard deviation by n. And this is just a matter of simplifying. And what do you get? You get that the mean of p hat is p, and the standard deviation of p hat is this. So they look similar because all you've done is taken the results from here and divided by n. And I've written it in a particular way like this. I mean, you could write it like this, you could write it like this. This is the standard, the conventional way we write that. These parameters now represent probabilities. So we retain 4 decimals when writing them. And notice, by dividing through by n, we're no longer dealing with a discrete distribution of x. So this was discrete. We converted it into a normal distribution for x. But now p hat is a sample proportion. It's a percentage, and it's no longer discrete. The values of p hat can be between 0 and 1. It's important to remember that. So although here we go from discrete to continuous when we make the approximation, here with p hat we're going from continuous to continuous. So we couldn't do this before. The binomial formula only worked on x as a discrete variable. Hopefully you can see this. Do I need to make it bigger? So what am I going to do with this? These results are all here. So stay with, keep this formula sheet nearby because it summarizes everything you need. So not only is x, this is a count variable, this is you can make, so I'm just making notes on here. So what it says is, when I have a sample and I'm looking to see what it is I'm looking for, the success, if that's the case, if that's the setup, then the possible outcomes take a normal distribution. It's predictable with a mean measured here and a standard deviation measured like that. And this is known as the sampling distribution of x. The possible outcomes of x are distributed in this way. So p hat, which is dividing x by n, also has a sampling distribution. The same logic, using the rules of mean and variances. Okay, so I've just recopied what's there. So this is the sampling distribution of p hat. The proportion of success is n independent trials. And what does it say? It says the expected value of p hat. What is the expected value of p hat now? What is the expected value of p hat? What does this tell us? So there's the theory has proofs supporting it, and using rules of means and variances, these are derived, the approximation established, and then empirical studies are done with computers to estimate the limits of this, these properties. And that's why they throw in the word large. This only works when you have large populations. So my question was, what is the expected value of a sample proportion? So for instance, we're going to conduct a poll and ask people, do you approve of wearing masks outside during this pandemic? And you poll in people, and you know the properties, you'd have to know this information. What's the chance that somebody is in favor or against? That's the probability proportion P. Then the count, the number of people that you expect to be in favor would be, so it's if P represents the people in favor, proportion of people, the likelihood that somebody's in favor, then you would multiply that by how many people. And that would give you the expected value, how many people you expect to be in favor. It depends on how many you ask. Here, what's the proportion of people you expect to be in favor? Well, it's just P. It's the true proportion. That makes sense. It's kind of confusing at first, but it makes sense that we want our estimate to have as an expected value the true value, right? That's what we want. That makes sense. So that's what this is showing. All right, so hopefully you'll get this either today or you'll review this to understand this. But if you understand it, it's way better to work with this topic than if you don't. All right, so what are we going to do next? We're going to... So I spend time in the notes solving the problems we already tackled, but using the population... the proportion, the sample proportion. So rather than saying, as I did in question 1 when I looked at this variable, what's the chance that x is greater than 23, I'm going to look at what's the chance that p hat is greater than 0.23. That's the question I want to solve. So first I check that n times p is greater than 10 and n times 1 minus p is greater than 10. And then I create the normal distribution for p hat and then answer the question. So my question to you is, should we get the same answer? So what did we get over here? We got this result here, 98.57. The question is, does p hat greater than 0.3 equals 98.57% as well? Yes or no? Gerardo says yes. Yes, they should be the same. We didn't do anything. I didn't do anything to the distribution I just renamed it. Rather than talking about the number of successes, I'm talking about the proportion of successes. Okay? So yes, it should have the same result. So I go through the process repeating these, and I think you should go through to make sure I got all the same things. It just looks a little different. And I'm using a subscript p hat now to distinguish between that for the binomial distribution, the binomial distributed variable x. So I use a p hat instead. So this would be the proportion, this would be the mean, this would be the standard deviation. I have to standardize and look all the way through. I get the same answer. And the same would be true for the ESP example. So you need to practice that. Convince yourself what's going on. This is a review of the normal distribution and bringing it home, bringing it up to date with the binomial. So they are related, they are linked, and they're linked through the property n times p is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10. So here you get the same answer as above. So let's see, let's try it. Why don't you try this one? I think I have the answers there too. Yeah. I give you answers for everything. Okay, let's just do this Catholics one, and then you can try the other one yourself. Okay, so let's see. Why don't you try this? Suppose the population is 25% Catholic. What is that? That is the true proportion of Catholics. That's not true in Puerto Rico. I think it's higher, right? Anyway, in a sample of 1,000, we expect about 250 Catholics. Right? Because that's the expected value. In other words, we expect a proportion of 0.25 Catholics. So I just repeat myself here. Find the probability that the number of Catholics in a sample of size 1,000 will be less than or equal to 260. So what I'm asking is to find the probability that the number of Catholics, x, so that represents the number, right? In a sample of 1,000 is less than 260. So we define x as the number of Catholics out of 1,000 population. And I know x is binomial with an n of 1,000 and a p of 0.25. And now I can check. So this is what I need to answer, but that's a lot of things I have to add. I would have to add equals x equals 0 plus probability x equals 1 plus probability all the way to probability x equals 259 because it says less than. Okay, I don't want to do that. I'm going to try to see, does NP equal is that greater than 10? Of course it is. And let's check to see, is n times 1 minus p greater than or equal to 10? Of course it is. It's going to be 750, right? Oh, let me slow down a second. Everybody's with me? You watching? So this is greater than 10. It has to be greater than or equal to, but if it's greater, then it's sure fine. So that's true. So because that's true, oh, thank you, less than or equal to. I'll put that there. Okay, so then I have to put it all the way to 260. Someone corrected me. Okay, so it's true, I can use the normal approximation, and I will assume that the population from where this sample came is large. Okay, so we assume the population is large. It's not just a small town or something like that. And then what I can do is say, so X is approximately normally distributed with N times P as the mean and N times P times 1 minus P square root as the standard deviation. So this one is 250, and this one is square root of N times 0.25 times 0.75, which when you put it together is how much? .33. So then with that, I'm going to go to the next page. You see, no, I got the wrong number. How did I do that so wrong? 13.69. Let's see what I got. Why do I have that number? 1,000. Oh, because I used 100. Yeah, 13.69. Okay. Erase that. And so let's just go to the next page. And here are the results. So this is what I'm going to use. This is the mean and standard deviation. Or these are the parameters for the distribution of X in approximation being normal. And I standardize this result, and I get the result here. So what this says is if I know in advance that 25% of people are Catholics, then in a sample of 1,000, I will find, the chance that I'll find less than 260 people is moderate, 76.73%. So you guys can practice. This is something you already know how to do, so just practice that. I'll give you a moment to see if you have any questions. So the only new thing is this check and making and calculating these parameters. All right, no comments. So let's go to the next question. The next question was, find the probability that the proportion of Catholics will be less than or equal to 0.26. So now this is asking the question about the proportion, not the number. So if I want the proportion of Catholics, then I need to use the sample proportion result, not the count. So what I need to do is I transform to the x over n statistic. I check that I can use this distribution to check, or to compute. And it's true, of course. If it's true for x, if it's true for the number of Catholics, it's true for the proportion of Catholics. I'm making the same calculations, n times p and n times 1 minus p. So then I have to get the parameters. The mean is just p, when I already have that. And the standard deviation is this, p times 1 minus p over n square root, which is this. So those are the parameters. So let me give you a minute to punch those in to see that you can get those. And now those are the mean and standard deviation, just like I've written here. And I use this notation with a p hat just to distinguish it between using the proportion and using the count. Using the proportion of successes versus using the number of successes. And then the problem changes to be less than 0.26 rather than less than 260, because 260 divided by 1,000 is 0.26. And I standardize using these new parameters instead to find the same answer. I'm going to get the same answer. So you don't have to do this twice. It's just to show you how to answer either question. If you're asked about the proportion of successes in a sample, you do it this way. If you're asked about the number of successes in a sample, you do it the other way. You should have the same answer either way. So as I said, I wanted you to look at that over the week because it's very tedious, and for me to go through it, you just need to make the calculations to, in effect, reviewing your understanding of the normal distribution. So I've repeated that these are approximations. They're not exact. Because all we've done is we fit a normal distribution on top of those spikes. So you can practice these other problems, and I want to start here. This is where I'm starting for today, even though it's an hour in. Any questions so far? Okay, so this is the last thing we're going to do before we delve into sampling distributions. No comments? So I say keep in mind the results that we've calculated so far are all approximations. Since binomial distributions are discrete and normal distributions are continuous, we would like the approximation to be as close as possible. So we could add what's called a continuity correction factor, and I use the notation CCF. Extending the area outward by 1/2 of 1 unit before standardizing it will correct for the imprecision of the approximation. So I teach this because it's important. If you ever read about statistics, I mean, lots of things, lots of times, many scenarios where you use approximations, and it's important to be able to read and understand what they're talking about when they make corrections. Okay, so this is just so that you see how this could be done in this case, or in any other case you can at least have a handle on it. So what we do here, this can be very intimidating looking at this, but I'm just showing you all the possible situations. What we're doing is we're thinking about this distribution over here. And what we're doing is, rather than if we want to go as far as 13, let's say, I want to say 13 or greater. Let's say we wanted to say the probability that x is greater than or equal to 13. So we wanted to find the probability of that using the normal approximation, because we don't want to add all these individually. So if you just took this area from here under the normal distribution, so you would calculate all that, right? If you're with me, you're going to be off a little bit, because in fact I'm going to make this thicker. Just have to remember. So this is what you're in fact doing. You're using the normal approximation and you're calculating all of that, doing what we just did. But in the normal density, in the binomial density, this is really up to here, right? So this 13 is actually, we actually building density around 13. So what we want to do is we want to add back this little bit here. We'll add back this amount so that we capture the whole bar of 13. And that's a better estimate, or they say it's exact. Okay, so what we're going to do is we're going to work with that over here and say, okay, so let's see, I have some examples. Let's do it here. Let's say it was, let's just stick with the 13. And let's say we want, oops, see, I always forget to put the thickness back. Okay, so let's say, for example, if we wanted to go, actually let's do the one I just talked about. So it's, what we did was x, what did we just do? We just did x greater than or equal to 13, right? So that would be this one here. So what you would want to do for probability x greater than or equal to 13 is like the one we were just looking at, is you want to contain the whole bar around 13, around the spike of 13 that created the density. So what you want to do instead is you want to go back to 12.5, and that's going to give you a exact calculation under the normal distribution, and that's called this continuity correction factor, not an approximation. So that's the idea of using the adjustment. So this rule is if you're at, and you don't have to memorize the rules, you just need to make the drawing. So just like we saw there, I'll just pull that back again. So rather than going from 13 forward, from this bar forward, I go back a bit. This is actually 12.5, and I go forward from there. So you would have to do the continuity correction factor and do x greater than or equal to 12.5 and calculate that instead. So as I mentioned, this is not going to be tested on the final, but for preparation for this test on May 1st, I might ask you one or two of these, so you should know how to do this. I'm not going to spend the whole test on it, but you should understand what I'm getting at here. So what other kinds of adjustments? Let me see if I can make this. I want to make this a little bit smaller. I'll just rewrite that. So what did I just do? This one was this one here. So it was, if the question was x greater than or equal to 13, then you would have to adjust with the CF of x greater than or equal to 12.5. If the question was x less than or equal to 13, then what? So this is just to note that you've made that correction. Well, if we're at 13, and you want to go less than or equal to 13, then you want to contain the whole bar of 13. You have to go up a little bit, you see, to get the whole thing. So that means you add, so it would be, the correction would be and then you would solve it. What about this one? What about x less than 13? So not including the 13. So in that case, you want to start I'm trying to draw this. Okay, so let's say that's 12. So these are the bars, right, of around the spikes to create area around a discrete distribution. And I want to go less than 13, so I don't want to include 13. So do you see that you have to start at 12.5 and go back? So you don't have to memorize these formulas, just make a sketch, or some people just get this, some people struggle. But I think it works when you make a sketch. So that would have to start to be everything but the bar of 13, it would have to start at 12.5, including 12.5 and going back. So notice, when we go to the continuous distributions from the discrete, we've got to be clear about the equals, less than, or equal signs. What about, so I'm not going to continue solving the problem. You have to do that using the normal approximation, the parameters and all that, standardizing, etc. Okay, so if x is greater than 13, what would be the adjustment? For x greater than 13, okay, so to be greater than 13, you want to start here and go forward, so it's at 13.5. So this would become okay. So any questions so far? Following what I'm doing? It's just it's nothing heavy there, just understanding I want to contain the bar or exclude the bar, not just look at the number 13. I need to look at the area around the spike. Now the next one is the most interesting, going from a discrete distribution to a continuous distribution. Remember, if we ask this from a normal distribution, the answer would be 0, right? The answer would be 0. So this is really interesting. I have to add some density. Let's add 5.5 on either sides, and now we have a continuous distribution, or we can answer it as though it's a continuous distribution, because otherwise this would have just been 0. We wouldn't have been able to solve this. Okay, so that you show like the approximation wouldn't even help us get this. We'd have to make this adjustment to get this value. So just to note, so this would have just been 0 if x was approximately normal mu sigma. So we don't want that. We want an answer. So what we do is we build density around it. I hope you're following me. So I'm not going to answer the question about 13. I'm going to answer the question around 13, the range of values, putting x in the middle between 12.5 and 13.5. And now standardize, etc. Okay, so that is continuity correction. I have some exercises that you can try, but that's it. Questions? I think that's interesting. I like that last result. So work on those, practice, do the homework, and bring yourself up to here. We're going to start with the sampling distribution material. Well, that was already sampling distribution topic, but I'm going to talk about the sampling distribution of x bar now, because we've talked about the sampling distribution of x, we've talked about the sampling distribution of p hat, so just to break it down, so this has been an SDS X, this is SDS P hat. I'm just trying to specify that each, when you solve problems, try and identify where it fits. Okay, so if you're struggling with all of this, these formulas that look similar, try and identify how you tackle the problems. Do we tackle it as a binomial? Do I tackle it as a sampling distribution? So trying to fit it into the 6 lines of formula that I have here. So this is where we are next, is number 3. So we're almost halfway done this formula sheet, which means we're halfway done the preparation for the final exam. For the test on May 1st, I'm just going to test you up to everything we do next week, and then for the final it'll be everything. All right, so here we are. This is known as SDS X bar. X has a mean of mu and a standard deviation of sigma. If that's true, then the sampling distribution of x bar has a mean mu and a standard deviation sigma over root n. Notice I haven't said anything about the distribution of x. I've just said if x has a mean mu and a standard deviation of sigma, the sampling distribution of the mean has a mean of mu and a standard deviation of sigma over root n. Okay, I haven't said anything about the distribution of x. I'm talking about the sampling distribution of x bar. I don't have any specifications on what the shape of x should be. I just know it's mean and standard deviation, and these are the results. So we're going to talk about this. What does this tell you? How can you summarize this result, and in particular this value? This is important as well. What can you tell me about that result? Let's take a 5-minute break and we'll start here, okay? Let's take 5 minutes. Okay, I'm back. So if you go to Moodle, you see that there are several videos, and that's most of them are on this topic, SDS. And I cover, well, I think I cover most of the pages of the notes. So you can review there if you don't like the way I explain things right now. And there's some things I will leave for you to do. I think this one. Oh, no. Uh-oh, what happened? This one. Oh, what happened? It turned on the volume. I don't know why that happened. Oh, I turned on my own video. Okay, that's not what I want to do. Okay, so let's, all I wanted was to show you this. Just turn on the video. Okay, so there's videos here. You should review those with this material, but I will focus on start here, SDS. So let me clear this up. Okay, so what we're going to talk about is the mean and standard deviation of the sampling distribution of X bar. Notice I use a big X. So this represents the random variable of sample means. So suppose that X bar is the sample mean of a simple random sample of size n drawn from a large population with mean mu and standard deviation sigma. Then the set of all possible sample means computed from all possible samples make up the sampling distribution of X bar. So I have loosely been talking about sampling distribution so far, saying that this variable, like X or P hat, we're calling it a statistic, but it's a variable as well that has a distribution. Okay, so P hat has a distribution that's approximately normal given certain criteria are satisfied. X, that's binomial, is also approximately normal given certain criteria are met. Here, X bar has a sampling distribution too. So although when we sample from a population, when we sample from a population, so this is a population like the grapes in the videos that you saw, we only get one sample if we sample, right? But theoretically, and this is an example of the empirical, like the kind of lab tests that are conducted for statistics. You can check if we create a population in a data set and you sample, and you can do that with statistical, or even Excel will randomly sample from a data set specified, or if you can create one and then sample from it, or you can use a standard one like a normal distribution. But here I'm just saying there's a population. There's no exact pattern. But we're going to sample from it, and we're going to collect these observations, x1 through xn, and we can compute a sample mean. But we could have done that for a different sample. We could go back and sample again, like return all of our results from the first one and sample again. So that would result in a different, so I'm calling them This is the first observation, second, up to the end, but they might be different from these, right? There's no reason they have to be the same. And I can calculate a sample mean, and it could be different from X bar, the first one. And you could do this again and again and again for all possible samples. So this represents all possible samples. And then let's say we have those results in an Excel spreadsheet, and we make a histogram of those results. So think about all combinations of the data, of the true values, and this is called the all possible samples. And from all possible samples, you can calculate statistics, and the one that we're concerned with right now is the mean, sample mean. So you have now a data set of sample means. You can make a histogram, and the question is, what would be the properties of that histogram? Or if you smoothed it out, what would be the properties of the density curve of the sample means? So if you started with a mean and a standard deviation given to you here, what can you expect, in a shape? What would you expect here from these sample means? Will they have the same mean? Will they have the same standard deviation? Would it have the same shape? That's where we're headed. Well, it turns out that if you collect a whole set of all possible samples and calculate all possible sample means, the sample means, so for example, applied example, when you go to your doctor's office, he may test your blood pressure, and he may test it many times. So now they have machines that will test your blood pressure 5 times and then report an average. You just have to sit in the chair and it will report the average of 5 attempts. Why do they do that? Why don't they just stick with one result? Well, that one result could be off. If you take several, if you took 5 and if you took 5 readings and averaged it, what do you expect? Do you expect any individual one to be more meaningful, or the average of the total to be more meaningful? So in the same sense, the average of averages is what would be the expected value. It turns out that taking the average of each set, those averages themselves are closer together, and that's my diagram here is just showing them more close tight together than the original values. Or I'm attempting to make that visual. Maybe that's not the best visual, but what happens is that the mean of X bar, so I have to distinguish between the other mean, right, is equal to the original mean. Okay, so the average of all of these averages should be the true mean. So again, beginning with a known population, known parameters, what do we expect from a sample? Well, that sample comes from a set of all possible samples, And the mean that you calculate from your sample comes from a set of all possible means. And you would expect that the one that you got, on average, will have the same mean as the original population. So there is a direct relationship. What about the standard deviation? What should be the standard deviation of all of these? Well, they're going to be centered at the mean, and they should be closer together than the original numbers. And it was established that it's closer together by a factor 1 over n. So that's a smaller number than the original sigma. So it's just a fraction, right? You're taking a fraction. Depending on what the sample size is, the greater the sample size, the closer the x bars are together, the sample means are together. They reinforce each other. So this is a smaller number. So closer together or more similar than So why do you want that? Well, you want that because what you're doing is trying to use the sample mean to predict as an estimator of the true mean. You want the sample mean to be a predictor of the true mean. So you want your sample to be just as good as any other sample. So they should all the sample means that are possible should be pretty close together. So that's good. So these results are the parameters of the sampling distribution of the sample means. The means should be good estimates of the true mean. So in repeated samples, on average, you will get the true mean. And it's very reliable because all the means of all possible samples will be closer together than the original values themselves by a factor of 1 over n. So the last thing is the shape. What do I expect in the shape of the sampling distribution? Now here, I haven't specified the shape. So what do we expect to happen? So I have some results here in an illustration, and I do have a video up about this too. Say the distribution of your variables like this. You know what? I almost don't want to do this because I don't want to contradict anything I said in the video. So actually I'm going to ask you to watch this video. I don't want to confuse you. Okay, they say things a little different and it's confusing. Okay, so watch this video that's provided in Moodle. And what I'm going to say, I'm just going to go back to the results. And the case is that if the shape begins regular, symmetric, bell-curved, normal, so if it's a normal distribution, then the sampling distribution of x bar will also be normal. And if the population distribution is not normal, the sampling distribution of x bar will still be normal as long as your sample size is large enough. So this is the result, set of results here. So if you begin with a distribution that's normal, with a mean of mu and sigma, x bar will be normal. So your sample mean will come from a normal distribution with the expected value the same, but a smaller standard deviation. So the sample means are close together, more reliable. If you don't start with a normal, so this is not, there's no shape specified here, but you know the mean and standard deviation, as long as the sample size is greater than or equal to 25, you get the same result in approximation. Notice, you get the same result in approximation. So you see, you really need to know your normal distribution because it's all hinging on that right now. I'm going to say approximately. So what do we do with this? This result is very important, okay? For the fact that knowing the shape is not important to be able to make predictions about the sampling distribution, as long as your sample size is big enough. The fact that this is true makes it possible. This is the bridge, an example of the bridge that I talked about. This implies that if I have a sample and I can assume these properties, then I can have a good chance of predicting my population mean without knowing it. So what if mu is unknown? Since in theory the mean of the distribution of sample means is equal to mu, we say that the statistic x bar obtained from any one of the possible samples is an unbiased estimator of the parameter mu. An estimator is said to be unbiased if the expected value of the estimator is equal to the true value of the parameter we are trying to estimate. So expected value, the average, right? Expected value. We will use this fact to determine the probability of particular outcomes so we're going to use this to make estimates of or predictions of what to expect from a sample, and then we're going to use it in inference to do even more. Another important result is that often we call this sigma over root n by a different name, even though it's the standard deviation of the sampling distribution of the sample mean. It's also known as a standard error, so you may have heard that terminology. Just to distinguish it between the initial sigma, which is a standard deviation. But it is a standard deviation. It's a standard deviation of the distribution of all the possible sample means. Okay, all right. So that brings us to this result. Let's say you want more precision. You want that the sample mean that you collect is really close to mu. In other words, the standard deviation or the standard error, the standard deviation of the sample means is very small. So how can you make it smaller? Well, if you notice the formula, depends on the sample size. So what you can do is make the variability smaller and smaller and smaller by increasing the sample size, because making this go up makes this overall number go down. And that makes it more likely that if you take a sample, then that x bar should be pretty close to the true mean. If you don't know it. So to cut the standard deviation of x bar in half, that is making the estimate more reliable, we must take 4 times as many observations, not just twice as many. What are we talking about here? Okay, so let's say I want this to be half of what it is. So you want a better one, right? You want this to be in half. Well, if you put that in half, then that would be the same as dividing this side by half. Which would be the same as everybody okay with me with this so far? So this would be the same as, to put it in the square root, you would have to square it. So that is the point that we're getting at. So if you want to halve the variability of the standard deviation of the sample means, that could be done by multiplying n, or not duplicating the sample size, but multiplying the sample size by 4. Okay, and in general, if I want to do this not just by half, but I want to do this as a fraction, so I use k, so it could be 1/10, 1/13. Actually, let's just do another number. Let's say 1/10. So if I want to do 1/10, it's 1/10 of this. I'm just repeating my steps. And then that would be sigma over 10. But because I can only affect, the only thing I can do to make this smaller is to increase the sample size. So how much should I increase the sample size? It's 10 squared. Or 100 times n. So in general, to get 1/k or a fraction of the standard deviation or standard error of the sample means, making them more similar, more reliable when I calculate one, I should increase my sample size by a multiple of k squared. In this case, it's 2 squared, or 4. In this case, it's 10 squared, or 10. Can you see all my calculations? Let's see. And that's what's in the box. That's what's said in the box here. Reducing the standard deviation of the sample mean to 1/k of its original desired value, we require k squared times the sample size. So that's important. There's exercises where you get to practice that. Okay. No questions? So we've learned a lot. This is known as, like we're working with the sampling distribution of the sample mean. I want you to watch this video, and then this result is the final statement. So what I've just talked about is true also, even if you don't know the original distribution. This result is known as the central limit theorem, and this makes it possible for us to study samples and attribute sample results as good estimates or as information about a population, taking the bridge back, as long as the sample size is big enough. This is a really important result. And I prove them all here. So you can read through those, you can ignore them. I'm not going to test you on them, but it proves all those results using rules of means and variances. I guess I have a video about it because I said that I do. I don't even remember some of the things I've done. But okay, so these are using the rules of means, sums of means and variances. Okay. And then we have some exercises. So let's work on these exercises, and then I'm going to leave it to you to practice all this stuff. I just want to check. This also has a video, so you need to watch this one as well. I'll say a few things before we end today about this. This is regarding statistical process control charts, so those are also available. So I just want to spend a bit of time solving these. So let x be a variable on some large population. Assume x is normally distributed with a mean of 13.8 and a standard deviation of 2.9. Let x bar denote the sample mean viewed as a variable calculated from simple random sample of size 9. All right, so what am I saying? I am saying x is given as normal with a mean of 13.8 and a standard deviation of 2.9. A sample of 9 is taken because we began with a normal distribution. The results carry to the sampling, the sampling distribution of the sample mean. This is also normally distributed with the same mean, but the standard deviation is computed as sigma over square root of n. This is the new standard deviation for the sample means. So this is going to be 2.9 divided by square root of 9. So put that number in there. So okay, so Gerardo asked the question about the 25. So he asked the question about what happens if it's less than 25. If it's less than 25, you can't do this. That's the best answer I have for you. So most of the time, I mean, I think all of the time I give you greater than 25, unless I'm asking you, I'm challenging you with something or other. If you, if you are not told, well, you should be told the sample size. The only way you can get around this, if n is less than 25, like in the example we're getting, and obviously n is less than 25, right? But the reason we can do this is because we started with a normal. The result holds. If you start with a normal, you get a normal, no matter what the sample size. But if you don't have a normal distribution to start with, you can't do this. Always have to have a sample size large enough. So if one situation where, let's say they don't tell you what it is, you would have to assume it. So let me add that point here to answer Gerardo's question. Gerardo's question is, what happens if it's less than 25? It might not be a great assumption, but to do anything, you have to assume x is normal. Okay? So if you're told that x is for sure not normal, you can't do anything. So you can't do this, you can't use this result if it's not normal. Okay, so I have some exercises like that, but that's good he asked me now. All right, so when we put 2.9 divided by square root 9, what do we get? Nobody's. Somebody check that number for me. Are you there? .9 divided by square root 9. Oh, well, that's just 3. What am I doing? 2.9 divided by 3. It's 0.9667. So this is where I'm going to apply my rule for 0.967. Hold 2 more decimal places than the original number, so I'm going to use that, 0.967. Now, that answers the first question. State the distribution of the variable x bar, include the name and the relevant parameters. Now, use that result to solve the question. Find the probability that x bar is greater than 15. So what we have to do is use this new distribution, not this one, to see the results of the sample. What's the chance that in a sample, the sample mean is larger than 15? So I can find that. I can standardize 15 and x. That will be minus 13.8 divided by 0.967. And that would be 1.24. Okay, Jaime, it says, yep, okay, so now what's the result? I'm only keeping 2 decimal places now because I'm going to use my standard normal table to check. I'm going to draw this out. 1.24 is about here, and I want this area, so I could compute it using the negative side, or I could compute it doing 1 minus. So for 1.24, I think I have the tables in the notes, no? I have the tables back here. So I can use 1.24. This is 0, 1, 2, 3, 4. So, no, that's right. 1.24. 0, 1, 2, 3, 4. So it's 1075. So if that looks slightly different from what I did before, you should be able to do that now that you know that these are the same, right? If you change the sign, you have to change this sign as well. So it's just the tail probability from the tables, and it's 75%, 10%, almost 11%. So what does it say? What does this mean? What's the chance if the mean is 13.8 and the standard deviation is 2.9? What's the chance that in a sample that the sample mean would be calculated to be greater than 15? Well, it's very unlikely, okay? With a sample size of 9, it's very unlikely. It's only about 10%. Oh, about 11%. In other words, it'll be closer than 15. Look here. Look how small the standard deviation is. The numbers are going to be very close to 13.8. 3 standard deviations even. So the results of the sample mean will be very close to 13.8, and 15 is far enough out. So that's only a 10.74% chance. Questions? What about these eggs? Here's another one. Try that one. You're so quiet. I don't know what you're doing. All right, let's see. I'm going to do this one. I'm going to leave the rest for you. And I'm going to move to inference for the last 15 minutes of class. All right, so let's see. The weight of the eggs produced by a certain breed of hen is normally distributed with a mean of 65 and standard deviation 5. Now think of cartons of such eggs as simple random samples. So this is like n equals 12 in a carton. So that makes it so we can calculate a sample, like an average of the weight of eggs in the carton. And since we started with a normal distribution, like a regular predictable distribution for the eggs, what about the average egg in a carton? So let's be clear what we have here. So this is going to be 65, and this new one is going to be smaller. It's going to be The new one will be the old one divided by square root of n. So it would be 5 divided by square root of 12. Whatever that number is goes there. And so let's be clear, this one is weight of an egg, and this is average weight of an egg in a carton. So they're related, but they're different. So this number is 1.44. Again, keeping 2 decimals more than the original values. Now the question is, what is the probability that the weight of a carton falls between 750 and 825. Notice these numbers are much bigger than what I'm dealing with because they're asking about the whole carton, not just an egg. So what do I need to do to answer this question? Hello, hello, are you there? Somebody? The question was, what do I do? Now you have the answers in the notes. I have all the answers provided to you, written up, typed up, but I want to see you critically think through this without looking. No clue. What we want to do is adjust the problem to suit our tools, right? We have this tool, we have this information about the sampling distribution of the sample mean, but they're asking me about the whole carton. This is the sample mean for the carton. So what I need to do is change the question. Rather than talk about 750 and 825, I need to divide those by 12. So I'm going to put those in my problem. I want to say, what's the probability that X bar falls between those? And now it looks like a better question. So what I do is I compute that 750 divided by 12 is 62.5. And I haven't done any other thing. I haven't done standardizing or anything yet. All I've done is reduce the problem to average weight as opposed to the weight of the carton. Eight 25, so this is 68.75, 68.75. And now I can standardize. 62.5 minus 65 divided by 1.44 and less than, this is now a z, less than 68.75 standardized. That. Okay. And then you simplify. I'll just go to the answers here. So you see the answers, solutions are here. You simplify it and then you calculate the probability. So the chance that the average egg is between 62.5 and 68.75. In other words, the carton's total weight is 750 to 825. The chance of that is very high, okay? If you have this information, 65 being the average weight with a standard deviation of 5. It means they're very, mostly, you know, between 60 and 70. So looking at this range is very likely that you're going to get the average weight to be that. More than 95%. Okay, so it's 11:30. I leave you with all of this to work on and struggle with, and you have all the answers. Watch the videos. This is regarding control processes, which is an application. I have all the answers there. And so what we've accomplished is we have learned the first 3 formulas of the formula sheet. And so what I want to complete for next week, hopefully we'll get through all of these, so that can be on the next test, and all that will remain is this, number 6 for the final. Well, I'm going to test you on everything, but I'm going to focus on at least getting through this next week. So where I want to start is here. What is this all about? So I'm going to open up the inference notes. That I had trouble opening. All right, so there are not a lot of videos on this in Moodle, a few. So mostly I like to teach this. So if you want to find other videos of me describing this, you can look in the playlist for other semesters. But this is where I start with inference. I look at proportions. So I really like to start, you can read all of that, I like to start here. This is a very good example. Look at that. It's like I predicted. It took 20 years for this, for these questions to hit home and be relevant. Okay, in a study with a new vaccine involving 53 lung cancer patients, 29 survived 5 years after surgery. The approximate 98% confidence interval for the true proportion of patients surviving 5 years after surgery with the new vaccine has which endpoints? Okay, so if you've taken statistics before, this sounds familiar. This looks like there's something here you can do. Let's piece apart what we've got. And in fact, with what I've taught you already, you should be able to reason through this if you followed what I taught you already. In a study with a new vaccine involving 53 lung cancer patients, so that's 53. That's the number. 29 survived. So tell me, what am I going to call these? In terms of the variables we've seen so far, what should I call these? What's 53? What's 29? So my hope is, with what I talk about today, you can get started reading through the notes and recognizing the pattern of this, the approach, and then work through the homework. Start working through the homework exercises. Nobody knows what's 53 and what's 29. 53 happens to be in a it's like our sample, right? It's like a sample. It's 53 is the sample, so this is N. And 29 acts like our count of successes, right? 29 survived. Right, big X. So from what we just discussed, that's the big X. That's the number of successes. Now look at here, inference. In inference, I don't know. I have N and I have the X, but I don't have the P, right? Because, well, I don't know. So let me make a note of that. So P, unknown, but that's what we want to estimate, because this is inference. Inference is a guessing, an educated guessing. So I don't know P. So what do I do? Well, the best guess we have for P is what we learned about the sample proportion. It's X over N. We already have something here. So this is 29 over 53, which looks like a familiar number on the left-hand side. It's 0.457. So this is our best guess or I'm going to call it the point estimator. It's going to be 0.547 because this is the sample result out of N. Now, we don't just, like, we know there's some randomness. We know that this isn't exactly, it's unlikely that that's precisely the proportion of successes with this new vaccine. This is just a sample. And there's some variability that we learned about just now. If we make the assumptions, well, we have a large population and that the N times P is greater than 10 and N times 1 minus, even though I don't know P, I don't know P, but I can make some assumptions to take the next step. And I'm going to take a leap and say that P hat comes from a distribution that's approximately normal with a mean of P and a standard deviation p1 minus p over n square root. This is what I taught you today earlier in the class. But I don't know p, so what am I going to do? I know that this is one of many, so this is a whole distribution of p hat. So what I'm going to do is I'm going to build a buffer around this guess. I'm going to build an interval of possibilities for p hat, or for p, sorry, around p hat. And what I'm going to do is I'm going to say, let's create an interval that goes, so I'm going to say, let's take p hat, and I'm going to make an interval around it. Remember how we learned to do that? We learned, like, take the mean plus or minus the standard deviation, right? We learned about that. Well, we're going to do that here. But notice p hat has this as its mean, and this is its standard deviation, and they both depend on p, which I don't know. So I'm going to appeal to the theory that p hat that I got is an unbiased estimator of p, and I'm just going to use it instead. I'm going to use it in place and call it the best estimate that I have. And then I'm going to build a buffer with some, I'm going to call, I don't want to put the symbol in yet, but I'm going to make not just one standard deviation. Remember, we can do 2 standard deviations or 3 standard deviations around the mean, right? I can do this. So remind me, here what proportion of observations I capture in 1 standard deviation. In 1 standard deviation, I get about 68% of the observations because of this. The distribution of p hats is normal. And around 2 standard deviations, I get about 95%. The standard since the distribution is normal. And for 3 standard deviations, I get about 99.7. All right, so these were just approximate values for 3 kinds of intervals. But what about, I go backwards, what if I want a 98% interval? How many standard deviations should I go to get 98% of the possible values given this sort of distribution? So you need to figure out, it's not going to be 1 or 2 or 3, it's going to be something between 2 and 3. So I can't just guess here because these are all between 2 and 3. But let's see, I'm going to use them. What I want is 98% of the observations of a normal distribution. What are the limits? In other words, how many standard deviations do I need to go around the mean to catch 98? So if it's 98 in the middle, that means that it's 1% on each side. So I can, let's write that in a different way. Let me make this bigger so you can see clearly what I'm doing. Let's make this my bad drawing. what I want is on this side, I want it to be 0, 1, 0, 0. So find the number of standard deviations I need to be away to get 1% below. So if I go into my tables, there are tables here too. Okay, this is the biggest file, but okay, let's see, 1%. Now there's two ways I can do this. I can go to the negative table here, all right, so we can use the standard normal of looking for 1%. Look inside and out. Right, so inside for 1% is here. This is the best one we have. So this is at negative 2.33. So like I said, between 2 and 3, this is 2.33 to be about 1%. So this is such a long chapter. So this has to be negative 2.33, and on the other side has to be positive 2.33. The second way you can do this to get even more precise is use a new table. So I'm going to introduce this new table. I'm going to talk about it more next class. This new table here, if you've never seen this before, this is the table for a t-distribution, and it turns out the t-distribution looks like the standard normal distribution. It's actually centered at 0, and we'll talk more about the distribution. It depends on the sample size, so each row is a different t-distribution depending on the sample size, and what happens is t eventually becomes standard normal the higher the sample size. And you see below here are what are called the confidence levels. This is basically that interval, the confidence of that interval that we're creating. And here's 98%. So to be precise to 3 decimal places, this is your best answer. This is Z. These are standard normal values. So any sample greater than 1,000, if you want to calculate t critical values, like Z scores are for Z, these T scores are for T, and with sample size greater than 1,000, it just becomes the standard normal table anyways. This value, 2.326, is also, but more precise, the critical value we need to have 98% of the observations within the interval. So, you can see you're going to recognize that number in a second. 2.326 is the value. They're about the same number, just one is more precise because it's 3 decimal places. Oh, I lost it here. I have to connect them. So, what we're going to do is make an interval, and I'm almost done so you guys can start going. I'm going to make an interval around p hat. I'm going to call this Z star because I have to pick the right one, and the right one turns out to be 2.326. And then I want to calculate the standard deviation. So remember, because we have to do this, right? Mean plus or minus standard deviation. But the standard deviation is this thing here. And again, I don't have p, but I do have p hat, which is a good guess of p. So I'm going to stick that in there. So it turns out I have to make this leaner. So this, notice I have the plus or minus, right? So that's the plus or minus here. This would act as the number of standard deviations I need to go away. It's called the critical value. How many standard deviations I have to go away to get 98% in the middle. When I put it all together, I get one of these. So I'm going to pick up here next class, and hopefully you can follow along. Please, if you didn't see the whole video, watch the whole video. But I'm going to pick up here next class. You're free to read ahead, but for now, at least minimum, study the SDS unit, okay? If you haven't finished bin, study bin. The next test is going to cover bin, SDS, and anything I do on inference next week. So I will stay on. If you have any more questions, I'll stay on for a minute or so. I don't want to stay on too long, because people just sit around seeing if other people have questions to ask, and I don't want to waste everyone's time. Okay, so I'm going to say bye for now, but if you have questions, I'll stay here for a bit.